Right, and away we go. Today we are talking about, well, you've already seen the name of the sections, velocities and rates of change. This is a warm-up for you guys, using those rules, except you'll notice we're using them in reverse. So pause, try it out, and unpause. Really, we're looking for what gives a derivative of 3x squared. A little bit of experimentation shows that you got x cubed for this one. If I was to take the derivative of x cubed, I would take that 3, slide it down, and then subtract 1 from 3 to get that 3x squared here. Another way to think of it is when you, whatever is up here, when you bring it down, you want to cancel it off. So you really just want to divide by whatever your new exponent is going to be. Like here, I know that I'm going to differentiate down from 4 to get a 3. So I'm going to want to, when I write down f of x, divide off that 4 before I undifferentiate here. So 5/4 x to the 4th is going to give me a derivative of 5x to the 3rd. As far as what gives me a 4th derivative of 0, that can be literally any cubic function, any cubic or lower degree, really. It's like if I was to look at, let's just put any number, x to the cubed. G prime of x is going to give me 3ax squared, where a is, again, any number. The second derivative is going to give me 6ax. The third derivative is going to give me 6a. And then any derivative after that, because 6a is a constant, is going to give me 0. Derivative of 0 is always 0. As I told you last class, 0 is the first function that you learn that is its own derivative. So what function has an nth derivative that is non-zero? Well, for number 4, any function that starts off with a negative exponent is going to work here. 1 over x. Because remember, when we take the derivative of that, we have to think of it as x to the negative first. Subtracting 1 gives us a negative 2. So it's never going to get down to that 0. An alternative for this one would be any rational exponent, like square root of x. Remember, we had to think of that as x to the 1/2. So when I take away that 1, it never achieves a 0 in our exponent, and therefore would never achieve a derivative that is a constant, which would have a subsequent derivative as 0. Alright, so now let's get into this whole thingy here. You would have had a homework quiz if this was a live class, but hey, we're doing distance learning now. Let's just uncover that. Originally, I didn't really want people to know that velocity was part of the section name, because the first activity that I had people doing in this class was listing rates of change. And one of the rates of change that I wanted people to get out there was velocity. Velocity is a rate of change. We have a bunch of other rates of change. If your velocity changes, that means that you are either speeding up or slowing down. You have acceleration. Other rates of change, really a rate of change is anything where the units involve the per. I've seen this one before, liters per flush. If you look at any toilet in your house, you will see on there so many liters per flush or gallons per flush. That's the rate of change of the water with respect to one flushing on the toilet. Really anything where the units have per in them. So let's look at a graph of displacement. This right here, we have distance versus time here. So we could think of this as miles per hour is what we're trying to figure out from this one. But this is displacement, again, miles and hours. In order to find the average velocity is the distance you've gone over the time that you've gone. So the average velocity brings us back to the secant slope, where you have the change in position over the change in time. Delta S over delta T. I guess it would be an appropriate time to tell you guys that whenever we're talking about position in this course, I don't know why, well actually I do know why, but in general, the function is defined as s of t. So again, average velocity would be your delta s over your delta t. Looking right here, you have delta s, delta t, f of t plus delta t minus f of t all over delta t. All different ways to find average velocity, but average velocity is not that interesting. Your speedometer is not going to calculate your average velocity. It will calculate your instantaneous velocity, how fast you're going at one particular instant, one moment in time, if you will. To find the instantaneous velocity, we want to change our delta t to 0. So this becomes, when we find our velocity, that's the derivative of position. That's something you might want to write down. Velocity is the first derivative of position. In my mind, this is what goes on. It's something that when I think of it as the differentiation ladder. That's not exactly what it's called, but you know, about appropriate. Excuse me 1 second. Oh, actually, you know what? I'll finish this up first. So velocity is going to equal s prime of t. And what we use for that is v of t. All right, so standard notation there is v of t is your velocity. If we have a rate of change of our velocity, how quickly velocity is gaining or not gaining, you have what is called the acceleration. Acceleration. And acceleration is going to equal, well, we'll call it a of t is the standard notation for it. It is going to equal the rate of change of your velocity. It is also the second derivative of your position. And then there's a third derivative of your position. I'm not lying here. It is called the jerk. The jerk is, I guess we'll just define it as j of t. It is a prime of t. The derivative of your acceleration, the rate of change of your acceleration is your jerk. It's also the second derivative of velocity. It is also the third derivative of position. All right? So we're going to actually go to a problem now. And that problem is, right here, throwing a rock up in the air. And I have to pause this, hopefully. All right. So I am launching a rock straight up with a velocity of 160 feet per second. And I have no idea why when I typed up this problem, I used what I call dum-dum units, those imperial units. Nobody in their right mind talks about feet per second. Nobody. The cool units to use are meters per second. So I just did some quick conversions. I've got the initial velocity of this rock is 48.768 meters per second. We want to be cool about it. So looking down here, I have this equation. This equation, if you've taken physics before, you recognize this equation. This is the equation for position of a projectile launched straight up in the air. All right? So let me give you some notation here. S of t, again, from the last page, you know that's position. S of t is equal to -1/2 g t squared plus v naught t plus h naught. A couple of notations in there. G is a constant, depending on what planet you're on, but that is the acceleration due to gravity. V naught, the sub-zero there, indicates that it is the initial velocity. So you would read that as V naught, and then you'd have H naught, or H sub-zero, that is the initial height of the object that you are throwing in the air. And of course, T is time. In this case, we can interpret time is measured in seconds. So we have a bunch of information that we can actually figure out here. To create this equation, we can just create an equation of S of t is equal to -1/2. We can plug in an appropriate g. We look here, we got 32 feet per second squared. No, that won't be good because I just denigrated the imperial units. The cool units are the metric units. Do we want meters per second squared or do we want centimeters per second squared? Well, looking from this, it's measured in meters, so we should probably do the 9.8 meters per second squared. So we'd have 9.8 t squared plus our v naught, our initial velocity, is how quickly the rock or whatever object. You can change this to whatever you want. Somebody got offended when I said it was kittens last time, so it's not a kitten. So when you throw a not kitten up in the air, that is the not kitten's initial velocity. In this case, our not kitten's initial velocity is 48.768 meters per second. So we slap that t on the end there from the equation. And then we just have to add on the initial height. Now, if you look at me as a person, I am not going to put my hand on the ground to throw something up in the air. I'm going to stand about here. So my hand, when I'm throwing it up in the air, is about 1 meter off the ground. Oops, that's not what I needed. I needed that. So plus 1. I'm just going to do some quick calculations. Like the real simplification that we can do is that half 9.8. Half of 32 would have been easy to do, but half of 9.8, again, if you're taking physics, you recognize that really easily. Here's how the equation is going to simplify all over the place. We got S of t is equal to negative 4.9 t squared plus 4.7868 t plus 1. All right, so I just took the equation, wrote it down again on a blank piece of paper so I had enough room to write it. So now what we want to know is how high does the rock go? Or the not kitten, I guess is what we're calling it. So for part A, how high does this object go into the air? Now, if I remember from Algebra 2 how quadratics are graphed, here I can see this is a quadratic because I've got that t squared and I've got a negative a value. The path of this, whatever it is going to look roughly like that. Any projectile motion, in general, follows a parabola up in the air. What we're trying to figure out is, what is this right here? The highest that the object goes. Let me see the exact phrasing that I had. How high does the rock go? So we want to figure out the highest. The technical term for that would be the maximum. Now, one way to do that, we happen to know from Algebra 2 that that is called the vertex of the parabola. We also know from Algebra 2 the formula for the x-coordinate of a vertex of a parabola. Everybody say it with me. X equals b divided by negative b divided by 2a. See, I couldn't even remember that well. I was being entirely facetious here. What we actually want to find out is, when does our velocity change course? So looking here, our velocity is positive. How do I know that my velocity is positive? Because remember, velocity is the slope of our position. I can see as I move from left to right, this side is going up. And this side, as I move from left to right, is going down. So looking over here, I've got velocity is positive. Over here, I've got velocity is negative. So what I really want to find out is, when is the velocity between negative and positive? And if you saw how I wrote positive and negative over here, you would recognize what number is in between positive and negative. And that number is 0. If only I can find out the velocity equation and set it equal to 0, then all of a sudden I can find out when the rock got to its highest point. Now looking here, again, we know from a couple of slides ago that v of t is equal to s prime of t. Looking up here, we've got some pretty simple rules to follow for our s prime of t. I mean, it looks to me like I'm just doing power rule. This first one right here, well, that's a constant, so I'm going to do negative 4.9 times, bring down my exponent. Negative 4.9 times 2 is negative 9.8. Negative 9.8, and then 2 minus 1 gives me that t to the first power. Plus 48.768, and the t just differentiates off because we've got a linear there, so 48.768 is just our derivative, plus 0. The 1 differentiates off entirely. So now again, there's my velocity function. I want to find out when velocity is equal to 0. Okay, equals 0. Let's see. Subtract 48.768 from both sides. We've got negative 9.8. T is equal to negative 48.768. Divide by negative 9.8. we've got T is approximately, and some of you will probably be faster at this than I am, because I just need to pull up my calculator and appropriately pull it up. We now want to find out what did we say? 48.768 divided by 9.8. I hope you guys will forgive me that I didn't put the negative there. 4.976. 4.976. 4.976. So it went 4.976 in the air, right? Okay, no. Here's where you really need to clarify your units. You need to make sure you use appropriate units. So in this case, it's T is approximately 4.976. T stands for, again, T is the time. So time, we look back at our units to figure out what time would make sense in this particular situation. And I can see, well, I've got seconds here, I've got seconds squared here. It looks like the time unit that I'm using is seconds. So this not kitten went 4.976 seconds in the air, right? That makes total sense. That is not a nonsensical phrase, is it? Okay, I'm being a little bit facetious there. This is not the actual height of, this is not how high the not kitten went. Whoopsies. That's not it. I want to get rid of that. To find out how high the kitten or not kitten, whatever it is, we need to find out what is S of 4.976. And here, all you have to do is plug 4.976 into the original position function to find out how high the not kitten went. Now, I'm going to cheat a little bit because I like using my technology. Oop, sorry. I'm going to use my calculator here. And what I am going to do, since I've got 4.976 is the last number pulled up here, I'm going to use my store function and store that as A. You'll see in my y equals menu, I already have the position function in there. So I've got 4.9 x squared plus 4.768 x plus 1. So now what I'm going to do, because this is easier for me, I'm just going to do y1 of that value that I just stored. Makes it easy to evaluate a function. And now I can see that this not kitten went approximately 122.343 in the air, right? No, that's wrong. I need to make sure that I'm using my correct units. So again, if I go back here, I can see from context, since we're using not dumb units, we're using meters as our units here. So this would be 122.343 meters in the air. And yes, I did throw this not kitten by hand. I'm very strong and I can make that go really high. Now, what is the application for this? Well, one, you sometimes want to know how high a projectile goes up in the air. Two, if I'm just being selfish on this, I might want to be able to graph this function. So now I can clearly see if I go into my window, I know I don't care when the not kitten is underground, so I can figure out my y min should be 0. And my y max, I'm just going to have to include that 122.343. So I'm going to make my y max 130. I don't have to do that guess and check kind of work to make sure that I get this parabola up high enough. Let's see if that, there is some ugliness there just in like I have too much of my axis there. So hopefully that's going to be figured out a little bit later. And I thought I changed my y scale to 10. There we go. That's better. I don't like how many tick marks were there. But you know, that's just preference. All right, let's take that away. Let's put this back up here. And let's look at what other questions we wanted to answer here. What was part B? Part B, what is the velocity of the rock when it is 256 feet above the ground on the way up? What about on the way down? Well, okay, we now know that the total height here, the height here was 120, let's just call that 122 meters, right? We now want to know what is the velocity at, oopsies, wrong way, at 78.029 meters. So we want to know what is the velocity at 72.029 meters. 029 meters. Part B, we want to know what is V of 72.029 meters, right? And that sounds like exactly what we wanted to do, right? Find out what is the height of this not kitten at 78.029 meters. No, that's not what we want. What we want to do here is we want to find out what the time is for 78. Can't write my 8s correctly. 78.029 meters. So instead of V of 78.029, I actually have to say 78.029 is equal to this function, is equal to S of t, and then find out what t value I have here. Now I am going to point out all of these numbers are really messy, so I happen to know that I am going to be using my calculator here. So here I can just pull up my calculator. Oops, not what I wanted to move around. I want to move around my calculator so that I can actually see this stuff here. So once I have my calculator out, in my y equals menu, I'm just going to put that 78.029 right there. And now when I graph this, I'm going to be able to see here's where the function is at 78.029 meters. All I have to do now is figure out what time that is. And to figure out that time, the easiest way to do this is to go second trace and go to your intersect. Your intersect is going to be at 1.969 seconds. So x is approximately 969. Or, now we're going to pause that for a second because there is something else that I want to do here. I don't feel like typing that number in again. What I feel like doing, instead, I can see now that my x value is at 1.969. I'm just going to take that x value and I'm going to store it as some arbitrary value in my calculator. I'm just choosing A. I'm overrating that A value from before because it really doesn't matter now. I already used that appropriately before. So now I need to find that other point of intersection. I found this one at the 1.969. Now I need to find this one. Again, you don't want to guess on it. You want to use your intersect feature. Get closer to that one. And it looks like we're at 7.984. 7. I know you guys aren't going to be able to see it behind my calculator. 984 seconds for both of those. Let me just move some stuff around on my screen here so you can see it appropriately. There we go. Whoops, not the one that I wanted to grab. There we go. We can move that right here. And there we go. Okay, cool. So now I'm going to take that 7.984 and, oops, I am going to store that x value as my value b. The only reason I do that is because now I know that I have my s prime of t, my velocity right up here. I can now take that velocity equation and I can plug it into y3, that negative, nope, wrong one, negative 9.8 t plus 48.768. And since I've plugged that in as y3, I can now go to my home screen and I can find out that the velocity at 1.969 is y3 of A. So I stored that in as A. And boom, my V of 1.969 is approximately 29.471. 29.471. And that's in meters per second because we're talking about velocity. My V of 7.984 is approximately, well, let's just do the exact same thing. I said second, enter, and just overwrite this with B. Negative, what? What? Negative 29.471 meters per second. So now I'm going to point out that I'm kind of playing a trick on you. I will point out that the two magnitudes are exactly the same. Magnitude meaning size of the number. The only difference here is one is a positive and one is a negative. And if you look at the nature of these two points here, there's the positive value, there's the negative value. So we have our positive velocity and we have our negative velocity. They happen to be at the same magnitude because of how parabolae work. They're symmetric on either side of that vertex. Pretty cool stuff happening here, right? Okay, so now we've gotten through A, we've gotten through B. Let's see what C does. What is the acceleration on at time t seconds? Okay, so let's just toss C. I hope I have enough room for this one. C, the acceleration. Remember, we know that the acceleration with respect to time is equal to the derivative of velocity, or the second derivative of position, however you want to think of it. In this case, happens to be nice to think of it as the derivative of velocity, because our velocity is negative 9.8 t plus 48.768. Now looking at that, that's a linear function. Linear functions have constant slope. Derivative is just slope of the function. So slope of v is negative 0.98. Sorry, negative 9.8. And in this case, we're talking about meters per second squared. Hey, that looks familiar, doesn't it? That was me being facetious, because it's right here. If you take the kinematic equation of throwing an object up in the air and take the second derivative, you will always get acceleration due to gravity. And that's regardless of what planet you're on. Because the only thing causing acceleration on this object is gravity. Oops, I meant to look at what D was. When does the rock hit the ground? So or the not kitten. When does the not kitten hit the ground? We want to know what that value is right there. And the best way to do that for part D, since this is such a messy equation, we could use our quadratic formula. But why would we want to use our quadratic formula when we have magic idiot box? We go into our trace. Now all of a sudden we've got our velocity equation in there too. Let's get rid of these two thingies. So we don't care about them anymore. We just care about the not kitten getting thrown up in the air. We can go to our second calc, and we're trying to identify a zero. Remember we did this in chapter 1. Left bound, right bound, and guess. And it looks like at 9.973 seconds, it's at -2 times 10 to the -11. That's essentially 0 right there. So 9.973 seconds. 9.973 seconds. Let's just make sure that we answered the question appropriately. The question should be, when does the rock hit the ground? So when does the rock hit the ground? The rock hits the ground at approximately 9.973 seconds. Now there is one little thing that I slide in here at the end. Speed is the absolute value of velocity. So speed, that comes into play right here on part B, where we found out that the speed at 1.969 seconds was the same as the speed at 7.984 seconds. So the speed was the same, but we had exact opposite directions. This is why when we talk about velocity, we have a vector quantity. When we talk about speed, it is just a magnitude for it. All right, whew, man, we're cooking here. So let's look at some other stuff here. We've got important to know the relationship between a position graph, velocity, and acceleration. And whenever you're giving your distance graph, it's important to just note what is the slope and what's happening to the slope as we proceed through this graph. So looking here, I can see as I'm going from left to right, well, it's pretty obvious that my position is going up. That means my velocity has to be positive. And anytime I have this, it's called concave up, where it kind of looks like a U. It's like the smiley face part of a parabola. That's where your slope is increasing. As I'm going from left to right, it's not just going up, but it's getting steeper and steeper. So what that's going to look like down here, I'm going to start at approximately horizontal velocity, and it's just going to go up until I get to about here. And right there, you can see that I have just like a linear component to this graph. So that part right there is going to be where your velocity is going to stay the same, all the way to right up about here. And you can see right there is where the velocity starts changing from started off getting steeper, then stayed the same. Now it's getting less and less steep. So what that happens is you're going to go down until right about here. Because right about there is when it gets so not steep that we have zero velocity here. And then all of a sudden, we have a turnaround. So that turnaround, we have, again, that concave down. We're gaining negative velocity here. So that means we're going to have to go all the way to right up about here. We're going to be getting more and more negative velocity until we're right about between here and here. That's where our velocity is, again, going to stay the same. And then here, we're going to be tapering off until right about here, where we have zero velocity. That takes a lot of practice to be able to do that. One thing that I do have available for you guys is this link right down here. It's actually a really fun thing to play with, and I'm just going to show it to you. I will link it in the Schoology page. But you can see, you can turn position, whoopsies, there I am. Hold on, troubleshooting, there we go, now it works. You can turn your position versus time graph on and off. You can turn your acceleration versus time graph on and off. And you're actually allowed to play with these right here. So you can actually take this, and each of these horizontal blocks right here are the same measurements on each of these graphs. So you can actually see right here, I've got a positive velocity that looks like this. And you can actually see what it looks like when you drag your velocity to like 0. You make your velocity negative at that point. It's just really fun to play around with, some really cool stuff. And something that's really fun to point out here, okay, really fun, is a sliding scale. You can actually take this value right here, and you can move your position graph up and down, and that does not change your velocity graph. Again, I'm going to put this link on the Schoology page so that you can use it, you can play with it. I think really the only way to make that cool is to play around with it. All right, so let's look at some, let's proceed to the next page here. Rates of change. So something that you will have to know, average rate of change versus instantaneous rate of change. Anytime I say average, that just means calculate the slope. Average, period, calculate slope. Instantaneous, period, use the derivative. So if you are calculating instantaneous, you have to be given what the function is, and you have to be able to calculate the derivative. So far, you don't have very many instantaneous rates of change that you can calculate because you don't have a lot of rules yet. And in general, it said there down at the bottom that the x is going to represent time. So here we have find the rate of change of the area of a circle with respect to its radius. That's difficult. How quickly is the area changing when r equals 4 or when r equals 8? And if the radius is measured in inches, what would be appropriate units for dA dr? Okay, let's worry about B and C later. Let's worry about A right now. Find the rate of change of the area of a circle with respect to its radius. So here's where Leibniz notation is going to come really handy for you. So d something, right? So we want the rate of change of the area with respect to its radius. So the rate of change of the area, that means that is the function that we're finding the derivative of. It is going to go in the numerator of the Leibniz notation. Now I wanted to break in there because, again, this is not a fraction unless it's convenient for us to think of it. It is convenient for us to think of it as a fraction right now. So we'd have dA with respect to its radius, dr. So what is dA dr? And to calculate dA dr, all you have to do is come up with an equation that is area in terms of radius. And I hope you all know that that is the area equation of a circle, or the area formula for a circle. So looking at that, I want to find the derivative of A with respect to R. So far, most derivatives that we've calculated have been with respect to X. We've done some with respect to T, but now we're just going to do the exact same thing, treat R like it's your variable. So looking at this, I've got pi as a constant, R is a variable. I want to take the derivative of R squared. Drop the 2 down and take 1 away. This becomes 2 pi R. Hey, cool. Let's see, does it ask us? Okay. All right, cool. So the rate of change of the area with respect to the radius is 2 pi R. So for part B, we want to find how quickly is the area changing when R equals 4. So what we would have to do is dA dr evaluated at R equals 4, which is just going to be 2 pi times 4, which is equal to 8 pi. We want to find out how quickly is the area changing when the radius is equal to 8. dA dr evaluated at R equals 4. That's 2 pi times 8, which is 16 pi. All right? Now the last question, if the radius is measured in inches, what would be an appropriate units for dA dr? Okay. The way that I think about this isn't really how you should write it out, but I look at this. If radius is measured in inches, my area is measured in inches squared. So you shouldn't really write it out like this. You would probably want to put a sentence that if the radius is measured in inches, appropriate units for dA dr would be inches squared per inch. Do not simplify this to just inch. It's important to note that as the radius increases so many inches, at a rate of so many inches, then the circle increases this, the area increases this many square inches. All right, so it's important not to simplify that. Now, you might be saying, like, why would I ever want to know this kind of thing? Well, this helps with any type of circle that grows. So you could be talking about like the profile of a balloon. If you're inflating the profile of a balloon, increasing the radius of that balloon, how quickly does the profile increase? Or you could make this analogous to volume, really. My mind on this one really goes to, in like 2008, there was that big oil spill in the Gulf of Mexico, and you could calculate how quickly the radius was getting bigger of that oil spill, and then you could use that to figure out how much bigger did the actual oil spill get, and then consequently, what my mind is going to, consequently killing all the ducks and that kind of stuff. This is another another application for it, talking about the rings in a tree. There's something about how like some of them are darker than others. Something about the rate of growth of the tree in healthy seasons and unhealthy seasons. I don't know. I'm not a biologist, so I don't know all this stuff. Economics. We have an application in economics for using these types of functions. Marginal cost is the first derivative of the cost function. It represents an approximation of the cost of producing one more unit. So if you have the cost function, which like C of X, where X is the number of units that you're producing, C would be the cost for producing that number of units, you can find C prime to find out how much it would cost to make one more unit. I'm not an economist, so that's kind of difficult for me to explain. Here's the like tangible example. We're gonna be making, what are we making? We're making stoves, all right? So let's just pretend that the cost for making C of X stoves is X cubed minus 6X squared plus 15X. X is the number of stoves. If you currently are producing 10 stoves, how much will it cost? How much will the 11th stove cost to produce? So one way that we can do this, we can find, 11th stove, you can find out how much it costs to make 11 stoves and take away 10 stoves, right? So just to drive home the ease with which we can use the marginal cost function, I'm just gonna try to do this by hand. This would have to be, let's see, 11 cubed minus 6 times 11 squared plus 15 times 11. I said 15 times 11 minus 10 cubed minus 6 times 10 squared plus 15 times 10. Okay, that's going to get really freaking annoying to do, especially if I have to do this multiple times at different values. And I even chose a friendly number. 10 stoves is extremely friendly to do here. So just to drive that home, again, this is extremely painful for me to have to do this. 11 to the cube minus 6 times 11 squared plus 15 times 11 minus quantity 10 to the cube. I guess I could have just called that. Whoa. Helps if you do 10, not 1 to the cube. I guess I could have just put it in as 1,000 there. 6 times 10 squared. Why do my zeros not be showing up right now? Whoa. Plus 15 times 10. Okay. So it looks like the actual cost to produce the 11th stove is going to be 220 units of monetary value. All right. Now let me show you marginal cost. 11th stove using marginal cost requires me to find C prime of X. Calculating C prime of X is not hard. I mean, the derivative of X cubed is 3X squared minus derivative of 6X squared is 12X. Derivative of 15X is 15. Okay, that's not that hard. And to find the cost to produce one more stove, we would actually want to find C prime of 10. So just look at the ease of calculation on this compared to this. I've now got 3 times 10 squared minus 12 times 10 plus 15. Okay, I'm not even going to touch my calculator here because this is going to be 3 hundo minus 120 do plus 15. 300 minus 120 would be, what is that? 180 plus 15 is going to be 195. Now I know you're saying 195 and 220 units of monetary value are not exactly the same thing, but here you're talking about producing massive numbers of stoves. So saying it's about $200 is in the right ballpark. The marginal cost doesn't give you the exact value it takes to, the exact cost it takes to make one more unit, but it gives you about the right cost. I think that was everything from, that was everything from this section. Now, a lot of these problems up here are going to be interpreting graphs, and that's one of the hardest things. So we're going to talk about that a lot tomorrow. Goodbye.